Swayam Prabha. Digital India. Educated India.
Now let us start with Unit 2. So far we discuss fundamental idea of matrices and a linear system of equation and based on the transformation. Now let us go with Unit 2. We are going to cover the topics are analytical geometry, that is a main topic. It has a subdivision, introduction to norms, inner product, length and distances with examples. Next one is ortho complement, then inner product of functions with the examples problems, and then orthogonal projection and rotation, a matrix decomposition and based on the determinant and the trace. Next idea is eigenvalue and eigenvectors with examples, and next one is a Cholesky decomposition and eigen decomposition and singular value decomposition, matrix approximation and matrix phylogeny. So, these are all the topics we are going to be covered. Now, the flow chart discuss about that. Start with the inner product space. So, if you want to understand the inner product space, we have to know what is the meaning of norm, and then based on the inner product we have to some classification also we have to do in the chapters. Followed with norm, we have to find the length. Once you know the length, whether it is a orthogonally normal or orthogonally projection, and if you have orthogonal projection, we have to find the angles and then rotation. So, these are all the most important that we have come across affine transformation. There we have to insert these ideas, and if you have no inner product, angle between the two vectors is most important. Based on the angles, we have to rotate it in all the directions. Once you know rotation, angle, orthogonal projection, we have to apply with the matrix decomposition. So, once you know orthogonal projection, we have to apply regression on linear. After completion of all these things, we have to discuss dimensionality reduction or not. So, these are all the ideas we are going to discuss. Now, for the norm, this meaning, you take x axis and y axis, we have to fix the length from domain to codomain or from one point to the another point. Then we have to fix a norm. Norm x1 stands for this length of this one is 1. Norm x2 stands for the circle with x square plus y square equal to r square, r is 1. Therefore, we can directly find out the norm of the circle also. So, these are all the different norms. Red lines indicates the set of vectors with the norm, left Manhattan norm, right Euclidean distance norm. So, this is the difference between what? Two different norms. Now, we have a definition. A norm on a vector V is a function from norm dot V maps to R, where x equal to norm x, which assign each vector x of the length norm x in R such that lambda in R. So, if you take a vector x comma y in V, the following holds good. One is absolutely homogeneous, that is norm of lambda x equal to modulus of lambda into norm x. Next one is a triangle inequality, norm of x plus y less than or equal to norm x plus norm y. If it is positive definite, then norm of x is positive and norm x equal to 0 if and only if x equal to 0. So, this is the meaning of norm of a vectors. For triangle inequality, you take two vectors a and b and that vector can be written as C is less than or equal to A plus B. So, next Manhattan norm. Manhattan norm is R power n is defined as x in R power n, where norm of x1 equal to summation of I equal to 1 to modulus of xi vectors x1 plus x2 plus x3 and so on xn. Simply sum them, that is a norm. So, modulus of dot represent its absolute value. The left panel of the figure 3.3 shows all the vector x in R square with a norm of x1 equal to 1. The Manhattan norm is called L1 is a norm. So, these are all the things you have to know. Next, Euclidean norm. Euclidean norm is x in R power n is defined as norm of x2 equal to root of summation I equal to 1 to n xi square. That is x1 square plus x2 square and so on xn square have to put root, and previously 3.3 is not a square, therefore, we have to do not put root. Either we can write this norm as x transpose x and computes the Euclidean distance of x from the origin. So, the right panel of the figure 3.3 shows that all the vectors x in R square, norm of x2 equal to 1, the Euclidean norm is also called L2 norm. So, this is the corresponding picture we discussed already. So, you know that this picture of norm is represented. Now, we have a dot product. So, we are very familiar with the dot product because A dot B equal to mod A mod B cos theta. Now, we may already be familiar with the particular type of inner product which is given by x transpose y equal to summation I equal to 1 to n xi yi. General inner product is linear mapping of the section 2.7 where we can rearrange the mapping with respect to addition and multiplication with a scalar. A bilinear mapping, omega is a mapping with 2 arguments and it is a linear in each argument. So, we have a vector space V, then it holds that x comma y comma z in V, lambda comma psi in R such that omega of lambda x plus psi y comma z equal to lambda omega x z plus psi omega y z, omega of x comma lambda y plus psi z equal to lambda into omega of x comma y plus psi omega x comma z. So, here 3.6 asserts that omega is a linear in the first argument and second argument says that omega is a linear in the second argument. Now, we have a definition. Let V be a vector space and omega is V cross V into R, be a bilinear mapping, takes 2 vectors and maps from 1 to onto and onto a real numbers. Omega is a symmetric if omega of x comma y equal to omega of yx for all x comma y in V, and omega is a positive definite if for all x in V negative 0. So, omega of x comma x is positive and omega of 0 comma 0 is 0. Next definition, let V be a vector space and omega maps V cross V to R, be a linear mapping that takes 2 vectors and maps them onto real numbers. Then the vector is a positive definite symmetric bilinear mapping from omega V cross V to R is called inner product in V, typically x comma y instead of omega of x comma y. So, the pair V comma dot is called inner product space with inner product, and if you use the dot product we call V of dot is a Euclidean vector space. Now, the inner product that is not the dot product, consider V in R tuple, 2 tuple, x comma y inner product represent x1 into y1 minus of x1 y2 plus x2 y1 plus 2 x2 y2. So, this is the inner product that is not the dot product. So, is an inner product, but different from the dot product, and this left to exercise to do it yourself. Now, we are going to discuss symmetric and positive definite matrices for all x in V negation 0 and x transpose Ax is always positive. Therefore, by definition of a symmetric and positive definite matrix is a symmetric matrix A in R power n cross n, n tuple satisfies called symmetric and positive definite or just positive definite if only greater or equal to holes in the equation, then A is called symmetric and positive semi definite. So, symmetric and positive definite matrices with example, consider A equal to 9665, A2 equal to 9663. You see these are symmetric matrices because above diagonal below diagonal are same and transport is same thing will come. So, A1 is positive definite because it is symmetry. Now, you take x transpose A1 x which is equal to x1 x2 of 9665 into x1 x2. Now, it is a bilinear equations. Simply it is what 2 rows and 1 rows and 2 column, 2 row 2 column and 1 row 2 rows and 1 column. Now, you have what matrix multiplication exists. So, we have 1 cross 1 matrix will come, that is only one equation will be arrived. So, 9x1 square plus 12x1 x2 plus 5x2 square. After simplify, we get 3x1 plus 2x2 the whole square plus x2 square. Now, whatever may be the value substitute positive. Therefore, in contrast x belongs to V negation 0, but A2 is symmetry but not positive definite because same technique apply x transpose Ax equal to 9x1 square plus 12x1 x2 plus 3x2 square, which is equal to 3x1 plus 2x2 the whole square minus x2 can be less than 0, that is for x equal to 2 comma minus 3 is a solution to the problem. So, this way we can denote whether it is a symmetric, positive, semi-definite or definite, something like that. Next, we have to go to the length. Norm of x is represent root of x comma x. According to Cauchy-Schwarz inequality, the inner product vector space V comma dot, the induced norm satisfies the Cauchy-Schwarz inequality of inner product x comma y is less than or equal to norm x into norm y. Now, we have a length vectors using inner product. In geometry, we are often interested in length of vectors. We can now use an inner product to compute by using the equation 3.16. Let us say take x equal to 1 comma 1. If we use the dot products as inner product with the equation 3.16, we obtain norm x equal to root of x transpose x equal to root of 1 square plus 1 square equal to root 2, right, as a length of x. Now, let us choose a different inner product x comma y. So, x transpose, what you have to do is main diagonal 1 and above below diagonal divided by 2. So, based on the previous equation. So, this equation you take it and symmetric we can convert, so that the equation may be reduced to like this, and then multiply them x1 y1 minus half into x1 y2 plus x2 y1 plus x2 y2. If we compute the norm of a vector, then this inner product returns smaller values than the dot product if x1 x2 have the same sign and x1 x2 is positive, otherwise it returns greater values than the dot product. Now, you have an inner product x comma x is x1 square minus x1 x2 plus x2 square, which is equal to 1 minus 1 plus 1 equal to 1. Therefore, norm of x equal to root 1 equal to 1. So, in a shorter the inner product than with the dot product. Now, we have a distance, consider inner product space d of x comma y equal to norm of x minus y equal to root of inner product x minus y comma x minus y is called the distance between x and y for x comma y in V. If you use the dot product as inner product, then the distance is called it as a Euclidean distance. So, then the mapping D such that V cross V to R of a inner product x comma y maps to D of x comma y is called a metric. So, similar to the length of a vector, the distance between the vector does not require an inner product. A norm is sufficient, and if we have a norm induced by the inner product, the distance may vary depending on the choice of the inner product. Now, for the definition of a metric, so metric D satisfies the following. If D is a positive definite, then D is always positive for all x comma y in V, and D of x comma y equal to 0 if and only if x equal to y. If D is symmetry, D of x y equal to D of y x for all x comma y in V. For triangle inequality, D of x comma z less than or equal to D of x comma y plus D of y comma z for all x comma y comma z in V. Note, at first glance, the list of properties of inner products and metrics look very similar. However, by comparing the definition of 3.3 with the definitions 3.6, we observe that inner product x comma y and inner product of y comma x and D of x y behave in opposite direction. So, very similar x and y will result in large value for the inner product and small value for the metric. Now, we are going to discuss the angle between the two vectors, also orthogonality of the vectors. So, assume that x comma x is not 0 and y is not 0, then the inner product x comma y divided by norm x norm y is nothing but the angle between the two vectors. It is always bounded between the minus 1 to 1. For example, in a figure 3.4, when restricted to 0 comma pi, f of w equal cos omega returns a unique number in the interval minus 1 comma 1. And therefore, there exists a unique omega in 0 comma pi. We have a illustrated example of cos omega equal to inner product x comma y by norm x into norm y. Next example, angle between vectors. Let us compute the angle between the vector x equal to 1 1 and y equal to 1 comma 2. Now, you see the figure 3.5, and where we use the dot product as the inner product, then we get cos omega equal to inner product x y by root of x comma x and y comma y, which is equal to x transpose y divided by root of x transpose x y transpose y, which is equal to 3 by root 10, and the angle between the two vector is across the arc of the cross of the 3 by root 10 is approximately equal to 0.32 radian, which corresponding to above 18 degree. Now, we are going to discuss orthogonality. So, two vectors are said to be orthogonal if inner product x comma y equal to 0. So, we write x is perpendicular to y. Additionally, norm x equal to 1 equal to norm y equal to 1. Therefore, the vectors are unit vectors, then x and y are orthonormal. Note, orthogonality is a generalization of the concept of perpendicularity to the bilinear forms and that do not have to be a dot product. So, in our context, geometrically, we can think of orthogonal vector as having a right angle with respect to the specific inner product. For example, you have an orthogonal vector minus 1 to 1. Consider two vectors 1 comma 1 and y equal to minus 1 comma 1 in R square. See the figure. We are interested in determining the angle omega between them using two different inner products, and using the dot product as the inner product yield and angle omega between x and y of 90 degree such that x is perpendicular to y. However, we choose the inner product x comma y is x transpose into 2001 of y. So, this way we can express the orthogonal vector. Now, we get the angle between the two vectors x and y, then cos omega equal to inner product of x comma y by norm x into norm y. So, norm x into norm y, x you know, y you know, simply inner product you do that, norm is a length, norm y is another length, simplify you get the minus 1 by 3 and then omega equal to cos inverse of minus 1 by 3 which is equal to 1.191 radian which is equal to 109.5 degree. So, x and y are not orthogonal, therefore, the vectors are orthogonal with respect to one inner product and do not have to be orthogonal with the respect to the different inner product. So, these things you have to remember. Next definition, orthogonal matrix. A square matrix A in R power n cross n is an orthogonal matrix if and only if its columns are orthogonal. So, that A you take it, A transpose you take it, product them, the resultant will be identity and as well as I is equal to A transpose A, which implies that A transpose equal to A inverse. So, the inverse is obtained by simple transposing the matrix. So, the transformation by orthogonal matrix are special because the length of the vector x is not changed. When they are transforming it using an orthogonal matrix A for the dot product, we obtain norm of Ax square equal to Ax transpose into Ax, which is equal to x transpose A transpose into Ax by associative property. So, for associative property A transpose A you combine together. So, A transpose A is I. So, x transpose Ix is nothing but x transpose x. So, x transpose x is nothing but norm x square. Moreover, so the angle between the two vectors x and y we measured by their inner product is also unchanged. When they are transforming both of them using the orthogonal matrix A, assuming the dot product as the inner product. So, angle between Ax and Ay is given by what, cos omega equal to Ax whole transpose into Ay by norm of Ax into norm of Ay, which is equal to x transpose A transpose into Ay by using the what formula, Ax whole transpose is x transpose A transpose, Ay keep as it is, then A transpose into A you multiply them, it become I. So, x transpose I into y is x transpose y divided by denominator, you have a what, norm of x can be written as x transpose A transpose A into xy transpose and then A transpose Ay. So, A transpose A is I and then x into x into I into x is x transpose x. So, x transpose x is norm x. Similarly, A transpose A is I and then y transpose y, I into y is y transpose Iy. Therefore, y transpose y will come, therefore, norm y will come. So, which gives exactly the angle between x and y. This means that the orthogonal matrices A with A transpose equal to A inverse preserves both angles and distances. Therefore, it turns out that orthogonal matrices define transformation that are rotation with the possibility of flips in section 3.9 and we have discussed of more about that rotations. That is all.